Perfect.
Good morning, everybody. Welcome for this new colloquium, Severo Ochoa colloquium at the IAA Instituto de Astrofísica de Andalucía here in Spain. And today we will have the talk by Dr. Federico Di Bruno from SkyEO, and he will talk about the protecting dark and quiet skies from satellite interference, challenge and mitigation efforts. So Dr. Di Bruno will be introduced by Anchon Alberdi, our director here. Anchon, please.
Okay, good morning and welcome to the IAA Severo Ochoa Colloquium Program. Our speaker today is Federico Di Bruno, as René has mentioned. Federico is one of the two co-directors of the International Astronomical Union Center for the Protection of the Dark and Quiet Sky from Satellite Constellations Interference, and representing both the SKA Observatory and the radio astronomy community. He works for the SKA Observatory in the role of a spectrum manager, a very important role in these years, specializing in the protection of the radio spectrum for astronomical research. Before his involvement in radio astronomy, Federico worked in the space industry with electromagnetic compatibility and radio frequency interference in communication and scientific spacecraft. This experience gives him especially useful insight and expertise for helping develop efficient mitigation strategies in communication with the commercial satellite companies to protect the sky for astronomical research. He is also working to create strategies to deal with contaminated data. Today, Federico will talk about protecting the dark and quiet skies from satellite interference. Federico, the floor is yours. Thanks for accepting to give this colloquium.
Bueno, Anchon, muchas gracias. Gracias por haberme invitado. Hola a todos, buenos días. Right, the talk is going to be in English, right? I'm from Argentina originally, but let's go in English. All right, first of all, thank you for having me. It's great to be here. And it's very nice also to see a lot of unknown names, which is great, right? I really like that. So I'm not preaching to the choir here. So hopefully we will learn some new things. All right, so let's get on to this because my presentation is a little bit long. And as usual, I started with some issues. Yeah, there you go. All right, so a little bit about me. Thanks, and Sean already mentioned this. So I used to work in the satellite industry. I'm an electronic engineer. Sorry, there was a mismatch there with the titles. I'm an electronic engineer. I know some about RF measurements and simulations. I used to work a lot with antennas in satellites, and now I moved to antennas in radio telescopes, basically, but more or less the same thing, just from a different direction for me. And I've been with 7 years with the SKO, and I've been 3 years with the CPS. So this picture shows you what I used to do in Argentina. That's a very nice radar we used to work with, satellite radar. And this is what I do now, right? So I did an interesting career shift where you see me there in Copwas with all the UN flags and in the mid site in South Africa with the Mercat antenna. Right? So that's more or less myself. I suppose you know a little bit about the SKO, but I'll do a brief introduction to the SKO, who we are and what we are doing. The SKO is an international intergovernmental organization, and we are tasked to build and operate two of the largest and most sensitive radio telescopes in the planet. We started our construction in South Africa and Australia in 2021, and we are expecting our completion in 2029. And you see there a picture of our different members and where we are located. I'll show you some few pictures of what we are building. Right? In South Africa, we are building the SKA Mid, which is a 197 fully steerable dishes, including the 64 Mercat dishes already doing science. And the frequency range of the SKA Mid will go from 350 megahertz up to 15.4 gigahertz in different bands. And our maximum distance, our baseline, will be 150 kilometers. The site in South Africa will be protected, or is already protected, by a radio quiet zone. So the radio quiet zone is established through national legislation in South Africa, and that zone covers from 100 megahertz to 25.5 gigahertz. And the site is located about 460 kilometers away from Cape Town, in a very remote area, because we need radio quiet, of course. Moving on to Australia, we have the SKA low in Australia. The SKA low is, of course, the low frequency part of the SKA. We will have 131,000 log periodic antennas spread across 512 stations. And the frequency range will go from 50 megahertz up to 350 megahertz with baselines of 74 kilometers, maximum baselines. Again, the SKA low is also protected by a radio quiet zone that goes up to similar frequency range than the mid, from 70 megahertz to 25 gigahertz. And we are located about 600 kilometers from Perth in Western Australia. Some pictures of low construction, which I could find. Hopefully, I'm sure you can find many more now online on what's going on, but I thought these were nice to see. So you see there on the right, that's the mesh of some of the stations in one of our clusters, and these are 30-meter stations. And on the left, you see them populated already with 256 antennas, each one of them. And if you want to imagine how does it look to work in there, you can see this. It's like a forest of log periodic antennas that people need to dodge. So it's quite challenging, but yeah, we are building already the stations there. And recently we got our first image of SKA low radio image in March, and using only 4 of our stations, so 1,000 antennas, we were able already to produce a radio image, which is showing a lot of progress. Is showing that we are able to calibrate the system and overcoming a lot of the challenges that we foresaw already in SKA low, right? So we are making progress. This is great. All right, so introduction done. Let's go to the part of the talk which you're here to listen to. And this is the agenda. The idea is to cover a lot of things shallowly. So hopefully you will have some questions and I'll be able to get there to the finish, and we'll have some time for questions. So let's make an intro to Dark and Quiet Skies. Then we'll talk about the CPS, the AU CPS. Then regulatory work, what we do at ITU and COPUOS, how we interact with operators, with satellite operators, and then some discussion of the possible mitigation measures we're working on. So let's go right into it. I hope you are, of course, aware of the changing situation we have in space with all these large constellations of satellites. Since 1957, we started using space with Sputnik, the first satellite up there. And about 2018, there were about 2,000 satellites in low Earth orbit. Now, moving on from 2018 to now, we have about more than 10,000 satellites just in low Earth orbit, right? This is about from 200 kilometers to 2,000 kilometers above the Earth. And these satellite constellations are aimed to do different things. I'm not going to go too much into detail on that, but low frequency, low latency internet, that's why they need to be very close. Internet of Things. They are using, of course, the fact that the launching cost is going down, and the space industry is migrating from the traditional space industry into more of like the rapid manufacturing industry, where they can produce satellites every day, more or less. So the industry is changing a lot in space. And the fact that satellites are in low Earth orbit means that the radio footprints are much smaller than, for example, a geostationary satellite, which is very far away. So that makes it that they need to have many more satellites to create the coverage of the Earth. So that's where we find these constellations of tens of thousands of satellites. And if we look at the plans in the ITU, which is one of the UN agencies that keeps a record or some proxy for a record of how many satellites are in space, the plans indicate that we could reach more than 1 million satellites in low Earth orbit by 2030. The reality is that all those are plans, right? Are companies or countries saying we are planning to deploy this constellation. Realistically speaking, we could be seeing around 100,000 satellites deployed or more, who knows, but this is just an speculation. But talking to some of the people in the satellite industry, they are talking about these numbers because, of course, many of these plans will never be fulfilled. So what is the effect of all of this, right? We have so many satellites in space, and what do they cost for our work as astronomers, radio astronomers, optical astronomers? So we have satellites in space, and they, of course, need to communicate with Earth. And the way they do, they send radio signals to Earth. These are quite strong signals in terms of radio astronomy, what we do. These are very strong signals because they need, of course, to provide data back and forward from the satellites. They use steerable beams or fixed beams, depending on the constellation. But that's one of the effects. The other one is, we have recently detected this a few years ago, not so recent anymore, the unintentional electromagnetic radiation, or UEMR, we call it. And this is basically radio noise radiating from the satellite. It's very different from intentional emissions that come from an antenna, which are intentionally used. The UEMR is just a byproduct of the operation of electronic components in a satellite. And then the last one is the one I will talk the least about it. I hope everyone is happy with that, or more or less. We can discuss a little bit, but I'll not touch too much on that. Is on the reflection of sunlight towards Earth. And that can, of course, impact optical telescopes and also, up to some point, the view of the night sky, because you start seeing lights that move in the sky. Okay, so I will focus on radio astronomy only, and let's go through the different parts and discuss it a little bit more. So starting on downlinks, so the intentional emissions of satellites, we need to do a little bit of intro on that. And that's mainly because of the ways we look at the radio spectrum, right? So if I ask how a radio astronomer or radio astronomy sees the radio spectrum, I see it more or less like this, right? We see the radio spectrum as different chunks of frequencies where we want to observe. We know that some physical phenomena happen in space, and emissions of some source happen in some of these bands, right? So we need to observe these particular bands to do science. This is the way we see it in astronomy. But what's the regulatory view of the radio spectrum? And this is always a picture that comes up in conversations on spectrum management. This is a graphic representation of the US table of frequency allocations. This is very similar in every country, but this one is particularly useful because you can see all the colors. And you see that there are many, many colors. And each one of these colors represents different users of the radio spectrum, and all these little bands are pieces of the spectrum that are assigned to certain user. And you see there the overlap, right? So we have a very, very wide range that we want to cover, for example, with the SKA, and you have a lot of different users, including in there a lot of satellite users, which is the ones that we struggle the most because they are above the sky. So zooming in a little bit on what this means, we can go into the L band, for example, in 1.4 gigahertz, which I hope some of you, if you're in radio astronomy, you will know what I'm talking about, the rest frequency of the H1. And if you see here on the left, which hopefully you can see my mouse, there on the left, you can see radio astronomy there between 1.4 gigahertz and 1.427. So putting it a little bit of focus, this, for example, are some of the protected radio astronomy bands that we have at the ITU. So these bands are protected by international regulation, right? So those bands need to be very, very clean to make observations. Okay, so I just wanted to say that just to clarify that many times when we in astronomy talk about interference in the general terms, sometimes it doesn't mean the same when you go and talk to a regulator or someone that works in spectrum management, because interference is signals that appear just right in these frequencies. Anything that is outside of these frequencies is not interference, sorry, in the terms of regulation, right? It can be interference for our observations, but it's not in the terms of regulation. So how does this all tie up with the constellations, and how do we bring it back to the real world? So all these big constellations of satellites, they use different frequency ranges, and it happens to be, unfortunately or not, that all of these frequency ranges that they are trying to use, like Ku band, Ka, V, and E band, and some others, are nearby or adjacent to a radio astronomy band, a protected radio astronomy band. As an example is the 10.6 to 10.7 gigahertz band. This is a primary radio astronomy band. And we have the 10.7 to 12.75 gigahertz, the Ku band. This is the one that Starlink and OneWeb and some other constellations use. So why is this very important? Because emissions or intentional emissions, transmissions of signals, they are not confined into a frequency channel, right? They have spurious emissions or spectral side lobes, depending on how you're used to talking about this. In the ITU, we call it out-of-band domain or spurious emissions, depending on the distance from the assigned channel that it has. And what's interesting about this is that, as I was saying before, it's okay to transmit in the satellite frequencies for the ITU, right? So we cannot really go and complain to the ITU if a satellite is transmitting in their frequencies. But it's very important that any transmission in their frequencies is not affecting any radio astronomy band. And that's what we work on at the ITU. So just to give you an idea of the power levels we are talking about, in-band power, if we think about Janskis, hopefully that rings a bell for you. If not, we'll just work on the relative difference anyway. So in-band power can be in the order of the million Janskis. Out of band can be in the order of 1,000 Janskis. And an astronomical signal can be less than a Jansky. And allow me here the loose this description of astronomical signal, because I know that we can go up to trying to find micro Jansky signals or less. But just to give you an idea of the spread of the numbers. And this is only thinking about one satellite. Now, what happens when you start seeing all satellites moving in the sky? Hopefully this video is moving for you. I see it moving for me, so hopefully it's moving for everyone. So you see there in the top box there, a view of the sky in azimuth and elevation. And this is just an example constellation of satellites that are moving around. And this red dot is symbolizing the radio astronomy antenna, one radio astronomy antenna, that is pointing at a particular direction, 30 degrees azimuth, 30 degrees elevation, more or less. And in the bottom panel, you see the receive power from the antenna coming from all the different satellites, right? So you see a baseline there, and then whenever a satellite is going nearby the main lobe of the antenna, you see these very large peaks. And this is in decibels, so the increase is about 100 times or more, right? When you have a satellite in there, right? So one important thing is that the whole receive power is a function of all the satellites. So you have there the integral that is in this recommendation of the ITU, but it's basically looking at all the satellites at every instant in time, and you need to integrate all of that to understand what is the total effect of these constellations in our telescopes. And the important thing about intentional transmissions is that beam encounters, right? So these very large peaks can saturate receivers, right? So depending, of course, on the headroom of the RFI that the receiver has. This is not the case so far for band 5 of the SKO, the one we are concerned in this frequency range from 10.7 to 12.7 gigahertz. So we are not concerned about saturation, but we are concerned about the integrated power that then we will see in that particular frequency range, because we do want to observe there anyway, despite of all the satellites. So this is what we are trying to do, right? To observe in all the band, which is much wider than the 10.7 to 12.7 gigahertz, much wider. So we want to be able to observe outside of that frequency range, and if possible, inside too, depending on the the RFI mitigation we can get. So that's the intentional part. What about the unintentional emissions? And here we need to make a little bit of intro to what unintentional emissions mean. First of all, the origin where these signals are coming from. As we were talking before about very well-defined transmissions in a certain frequency band, right? We say 10.7 to 12.7 gigahertz, all the transmissions are there. Well, for UEMR, for this unintended effect, the origins can come from wherever, right? It's basically a byproduct of the operation of an electrical device in the satellite. So whatever is there, as switching signals, clocks, high-speed internal communications, power supplies, even the thrusters, ionic thrusters of the satellites can produce this. And is normally irradiated just by the structure of the satellite, by a cable, by the solar panels, whatever. And thinking about the spectral signature, it can look more or less like this picture there, normally uncontrolled, right? So you see a broadband thing that depends, of course, on the characteristics of the signals we're talking about, but normally it's broadband, so it doesn't have a defined carrier. It's repeatable in a broad sense, because if you have a series productions of satellites, like the ones we are talking about here, of these very big constellations, all satellites look the same, at least within one constellation, with some variations on versions and things like that. But it should be repeatable, right? If you have a power supply that is noisy, it will be noisy in all the different satellites because it's the same one, more or less. And it's usually in low frequencies, right? So all these type of emissions, they normally go below 1 gigahertz. I said usually because it can happen, right? You can have some clock in 5 gigahertz, and if it's not properly shielded, it will also radiate in 5 gigahertz anyway. So what we did some time ago is we postulated the possibility of having UEMR from a satellite. So we did discuss this back in 2021, I think it was, in one of these Dark and Quiet Skies meetings. We said this would be possible with some colleagues from CRAF also. And a few years later, we used the LOFAR telescope in the Netherlands to actually observe it. So yeah, not a nice thing to be right. But anyway, so we were able to measure this in low frequencies, in the LOFAR high frequency, which is between 110 megahertz and 188 megahertz. Sorry about that. And you can see here on the left an animation of one satellite going through the 91 beam arrangement of LOFAR. What we did is basically we left the telescope looking in a fixed direction in the sky, and we waited for the satellites to go in. I see I'm raising my hand. Yeah. And on the right, you can see the frequency characteristic of these transmissions. And the interesting thing is that all these panels are frequency ranges, right? The first one goes from 110 megahertz to 120, more or less, and you get all the ranges of LOFAR high. But if we zoom in, you see that the horizontal axis is time. So if you are waiting in one of these beams, you're waiting for the satellites to go through, you see nothing, you start seeing the side lobes of the antenna response, or you can see it here as integrated. And when it's zero, the satellite is going through the main beam of the telescope, you get a very strong signal. And this is the frequency characteristic that you see in all the different panels, right? So this particular satellite was emitting RFI in here, or unintentional emissions, in all these frequencies. The question is, what is the maximum UEMR permitted by satellite? Because one thing is to say that we can detect a particular satellite that has this noise if we observe it, but another one is saying what is the ensemble of all these satellites, that they all look the same. what is the effect of this ensemble. And it's not exactly the same, right? Saying that I can pinpoint a satellite with a very sensitive radio telescope and say, well, I detect this noise, which we can do it for the International Space Station, and that will surely be very strong because it's not built to be radio silent. Or you can do it with any other satellite that is out there. With a geostationary satellite, maybe they're very far away, but you can do it with those. The thing is, if you don't point your telescope directly to the International Space Station because you actually want to observe a celestial source, maybe the emissions from the ISS, you don't really care. It's not a problem. The thing is what happens when you have this cloud of satellites all around the Earth, and you're trying to observe somewhere, and they just keep going through your beam over and over and over, and that starts to integrate. So this is what we looked at using this equivalent power flux density method that is developed by the ITU, which was in the other recommendation I showed before. If you're interested, you have the number there. And we use this method to understand how this equivalent power flux density behaves depending on the numbers of satellites. And of course, it's strongly dependent on the constellation size. So we ended up doing this study looking at the maximum UEMR permitted per satellite. So that will, in our minds at least, that will help operators of satellites to say, okay, I have a constellation of 1,000 satellites. How much this particular satellite can radiate in a radio astronomy band? That's a key word to use there, in a radio astronomy band, because what we found before, what we found before was this emission in a radio astronomy band, 150 megahertz to 153 megahertz. This is a radio astronomy band. So that's our main point, right? These emissions are happening in a radio astronomy band, and depending on the number of satellites, depending on the characteristics of the transmissions, the characteristics of the equivalent antenna pattern of a satellite, which we said is not an antenna, it's just the structure, how that's going to go. We ended up with these numbers, and you can clearly see a trend. The larger the satellite, the lowest the emission they should have. Right, so that's something we are working on. Unfortunately, this is not regulated in space, so spacecraft do not have a strict regulation as we have on Earth. For example, for our electrical devices, they have some regulation that says this is the maximum level they can emit. That doesn't happen in space. And especially, this is not public information. So we cannot say, like in the intended case, we cannot say this particular satellite transmits here and there. That doesn't happen. Right, so I think I need to speed up a little bit. So what are our multiple responses from the SKO, what we started doing? So we worked on the regulatory side. COP was in ITU. We paired up joined with the IAU, the International Astronomical Union, and the US NOAA Lab to create the IAU CPS. And we are having interactions directly with operators or owners of constellations. So let's go quickly through each one of these. Starting with the CPS, hopefully you are a little bit familiar or have heard about the CPS before. The CPS is a virtual center that we created, co-created with, or co-sponsored, I think is a word, between NOAA Lab and the SKO under the IAU. And what we do here is we promote collaboration among all stakeholder communities that are involved on dark and quiet skies. So we have more than 400 members that cover astronomers, satellite industry, amateur astronomers, astrophotographers, communication professionals, policy professionals, and others, right? And also normal general people interested in protecting the dark sky. So we have a lot of different stakeholder communities, and the idea is that we are trying to create a space where people can share ideas, concerns, and trying to put that at a plain level, which is challenging, but we are getting there. We also do research on the impact of satellite constellations, and we also produce software and information to deal with this, right, and trying to find mitigations, working in collaborations with industry also. So this is our membership map, more or less. We cover a great part of the world with people involved or interested in the CPS. And we divided the work in 4 areas, right, which we call the hubs, 4 hubs. So we have Community Engagement Hub, which is working on outreach and also receiving information or opinions from the great stakeholder groups. Community engagement worked on producing educational videos that are already in YouTube about SATCONs, about satellite constellations in general, starting from what is a satellite constellation to how it impacts dark and quiet skies and other things. We are working on a planetarium show, right, trying to expand on this idea of showing how the sky may change due to the satellites reflecting sunlight mostly. And we are working with engagement with the wider community, right? It's not only the professional astronomers, the satellite constellations, but also what the wider community, minority communities think about all of this. Then we have on the right, top right, SatHub, which is dedicated to observations and software development. So there we have the most active community, mostly of astronomers, working on observation campaigns, for example, so using telescopes to do particular observations in communication with the industry, right? So we have, for example, Amazon Kuiper launched a satellite, and SatHub is in communication with them, saying, all right, how many satellites you launched, this, and that. Right, we are going to make measurements, and they discuss the results, and that's working quite well so far. We do peer review publications on the topic of satellite constellations, so dark and quiet skies. We do software development. So far, we are working on SCORE, which is an observations repository. SatChecker is a software to work on satellite ephemerides, to know exactly where the satellites are, to do mitigations on our side. And we have a very, very active community on Slack, right? So we use Slack, and you can see the Slack lights up all the time from SatHub, so that's very active. Bottom left, we have Policy Hub. So policy is mainly looking at all the national and international regulations related to dark and quiet skies. So they have published recently a very thorough work looking at this, different countries and how they treat dark and quiet skies, or the protection of dark and quiet skies. They have just also published the CPS positions paper, which was not only developed by the people in Policy Hub, but also with input from the wider community of the CPS. We work on responding to national consultations on space law. So whenever there's a space law in a country and they are open for consultation or having inputs, we put inputs there through the IAU. So the mechanism is the CPS suggests the IAU to put a response to these national consultations. We also advise the IAU in UN COPWAS, and we liaise with the expert groups that work at the ITU, so that we have also the connection between the work in the ITU and what the CPS does. And last but not least, the Industry and Technology Hub, where we have a large group, about 16 operators in there, owners of satellite constellations, and they discuss in there their mitigations for dark and quiet skies. So they have a technical advisory group where they regularly meet, and we are also working on an astronomer guide program where we are trying to pair satellite constellations or operators with an astronomer. So the idea is that we can create this very close relationship, maybe even under an NDA if they want, to be able to discuss more one-to-one on the solutions that they are looking for and how the effects are on astronomy and so on. So we have, I think it's about 6 or 7 astronomer guides paired with different of these very large companies, and they're working together. And of course, working on the awareness raising with industry, right? Industry was, of course, a few years ago, was not aware of all this, that this effect was going to happen. So this is always a work in progress to try to explain to industry how astronomy and the night sky can be affected by all these effects. Right, so that's, one more thing about the CPS. Please, if you're interested, go to our website, cps.iau.org, and you can apply there for membership, and you can find ways to participate and get more involved if you like. Good, now checking the time, I really need to hurry up. Going into regulatory side, so in the ITU, we worked on registering our telescopes at the ITU, so SKA Mid and SKA Low are now in the MIFAR, the ITU registry, where it says all these radio stations are working in these different bands. So we have now that done, which is very important. We're also working in an agenda item for the World Radio Communication Conference in 2027. This is the big conference of the ITU that basically changes the international treaty that defines how the radio spectrum is used, right? So all these bands with little colors, this conference can modify it, let's say, and there is an agenda item in there to study and propose ways to protect, in particular, the SKA Mid and ALMA from satellite constellations. So we are working on that, doing technical studies at the moment to provide to this agenda item. We are also working on a report on UEMR in the Working Party 7D of the ITU, which is dedicated to radio astronomy. So we are trying to get a report on UEMR approved in there. It's proving challenging because, as I was saying before, UEMR is not defined, not very well defined in the framework of the ITU. The ITU works with intentional transmissions. So UEMR, it's a thing in the middle, because while it's not intentional, it could produce radio frequency interference in a radio astronomy band. So that's what we are arguing there in Working Party 7D. We are working with South Africa's regulator, of course, and we're working on other agenda items such as direct-to-cell, use of spectrum from the moon, and the protection of radio astronomy above 76 gigahertz, which I didn't put the number, sorry. And interestingly enough, the ITU is also working on space sustainability in its study group 4, which is dedicated to satellites. So we are also trying to monitor that and seeing how that evolves and see if we can also get something on astronomy in there. Moving into COPUOS. COPUOS is the Committee on Peaceful Uses of Outer Space. So it's a UN committee which deals basically with all the peaceful uses of space. And recently we obtained an agenda item in there, or we were able to put something in there. Lots of work from the IAU, from some delegations like Chile and Spain, from COPUOS, helped us a lot. Also SKO, the European Astronomical Society, ESO, we are all there as observers in there, so we worked a lot. And we got this agenda item in the Scientific and Technical Subcommittee of COPUOS, of Dark and Quiet Skies. We also created what is called the Group of Friends for Dark and Quiet Skies. So this is a group of mostly countries and some observers. It's about 19 countries, I think, at the moment, where they just meet and strategize about what to do in COPUOS and how to protect dark and quiet skies. With the SKO, we are planning a UN SKO workshop on dark and quiet skies in Vienna, in Austria, in December, 9 to 12 of December. Soon the communication will come out. So we are very excited to be able to organize this. And if you are wondering what's the possible outcome of COPUOS, it's not easy, but the idea is that COPUOS can produce either high-level declarations or guidelines on dark and quiet skies. We can discuss a little bit more of that if you like. And quickly, what are we doing with satellite operators? So while we do all the regulatory stuff, we are also very aware that regulatory things go very slow. So we are talking directly to operators. So we are talking to operators in the US, in Canada, UK, European Union. IRIS² is just starting in the European Union. So we are also talking to them as early as possible, right, to raise the awareness about dark and quiet skies, and also to China. We just started, it's slow, but we are in conversations with some of the constellations in China too. Our goal there is informing about astronomy, about dark and quiet skies, about in particular SKO, our radio quiet zones, and the potential effects of both, right? Their downlinks and the UEMR. We are trial testing some techniques like boresight avoidance. I'm going to talk a little bit about that later. So we tried this at the Onsala twin telescopes in Sweden with very good results. And we are having technical discussions on potential UEMR with all operators and owners, right? UEMR is a thing that if the builder or the designer of the satellite thinks about it early enough, it can be mitigated very cheaply, in quotes, but it can be cheaper than mitigating it at the end when the whole satellite is built and suddenly you find that it has emissions in a radio astronomy band, for example. So that's what we are trying to do, is raising the awareness as early as possible on the topic of UEMR. So what are some of the mitigation strategies? Almost done. So technical mitigation strategies for strong downlinks. As I said at the beginning, the focus, first of all, is avoiding to saturate the receivers, right? If the receiver saturates, we just lose the whole band, at least for the time that the interference is there, like when the satellite is going through the beam, for example. Some of the things we can do is this idea of boresight avoidance that you have here on the right. The idea of boresight avoidance is that there is a communication between the telescope and the satellite constellation, that we can inform them where in the sky our telescope is observing, and they have a way to change the software of their satellites so that when the satellite is going through an inner cone or something very close to our main beam, it can turn it off or turn off the emissions in a particular channel. And then when it goes out of this red inner beam, the satellite can transmit in certain channels, but away, as far away as possible from the telescope, right? And when it's really, really far away, in principle, it could even transmit closer to the telescope. We are still debating on this beam here that transmit directly to the antennas. So yeah, take it with a pinch of salt. But that's the idea. So we did the tests in Onsala, and we saw a mitigation in the order of 30 dBs or 1,000 times less RFI than without it. So it looks very promising. It doesn't mean that we will solve everything with this, but it looks promising. Also, we are talking about no beams towards the antennas or national licensing conditions. As you see here in this plot on the right, these red circles is the idea to say, well, as close as possible to the antennas, there shouldn't be any beams. But as you can imagine, we're always balancing the fact that there are towns around the site, and these towns or small farms also will also require connectivity, and this is a very remote area, so there are no fiber connection in there or good internet connection. So it's always a balance between connectivity for the people, and this is something that the country wants to do also, but also protecting astronomy. So we are trying to work that with the regulator, especially in South Africa. Interferometry, of course, we are building 2 very large interferometers, can further attenuate RFI, and we are just doing now the simulations on interferometry, and we are seeing more than 20 dB or 100 times attenuation, of course, depending on the baseline, right? The length of the baseline has more or less attenuation. And we are working on software to predict the satellite positions, to allow flagging, for example, right? So we are, of course, planning to have that for the SKO. And the CPS, as I mentioned before, is already working on software for this, which in principle we could implement also in the SKO. And quickly on UEMR, this is a bit more challenging because it's not so well understood. So we are still working on that. So we are continuing the observations. of the emissions. So you'll see a few papers coming out from the different low frequency telescopes like MWA, NENUFAR, and others. We are creating a group on UEMR under the CPS. So if any one of you is very interested in UEMR or you would like to work on that, get in touch because we are creating this group. We are in discussions with, in particular with Starlink about their emissions, and we are working with them to see if they find ways to mitigate the emissions of the satellites that are going to go up, right? The ones that are there, there's nothing we can do. But the good thing is that the lifetime of the satellites is not very long. So in a few years, they will just come down and they will have to be replaced in the model that they have. The idea is that the ones that replace this maybe can be mitigated. So we are working on that, awareness raising, continue on the regulatory work. This is very important because we do have a regulatory hook on UEMR. So we are working at the ITU and also on COPUOS and same software mitigations on the telescope. All right, so quickly, so we have a little bit of time for questions. So what we discussed in summary is on satellite mitigations. We are focusing on minimizing and awareness of UEMR. As I've said, the radio astronomy bands in there help to have this discussion. For downlinks, we see that broadside avoidance can be a way to minimize or mitigate the level of RFI. It doesn't mean that it will disappear. It will be minimized, and also interferometry will help. On the telescope mitigation side, we are continue doing our simulations / observations. Right? We have done a lot of observations that confirm our simulations, so that's good. Working on satellite position prediction, online RFI detection for the strong RFI. The prediction and avoidance could work even for RFI that we don't detect, for example, and interferometry. And in the CPS, we'll continue on collaboration and awareness raising and observations and developing software. And last, on the regulatory side, we are still working, or we will continue working, of course, on the national protections in operator licenses so that we can get conditions for the licenses for satellites to operate in countries that says things like avoiding pointing beams to radio telescopes or having these ideas of dynamic coordination like broadside avoidance, for example, in frequency or in spatial domain. In ITU, we work on the agenda items. We worked on a list of radio quiet zones, which I didn't mention. And we work on this resolution of space sustainability. Maybe we can get something there about dark and quiet skies. We'll see. And in COPUOS, hopefully we can get a high-level statement or guidelines on dark and quiet skies. And with that, yes, I think that's all. So thank you very much for your attention. And any questions, happy to answer. Thank you.
Thank you so much, Federico. This was very, very interesting to see. And I'm very excited that we did invite you because this is so important. I have a load of questions myself, actually, but I think I'm going to first see if anyone in the group here, and also there is a few people on the YouTube. So YouTube people, you can write your questions in the chat. And those of you here, you can raise your hand. And to start this all off, actually, I'm going to pose my questions because then, let me see here. I'm just going to try to show everyone. Okay, I have loads of questions here coming up. I'm going to start with Lourdes. Do you want to start?
Yes, hi. Thank you. Thank you, Federico. This is a very, very challenging issue, and also has lots of room for scientific diplomacy, etc. I was wondering, in this complex political situation in the world, we know in which part of the world, is this making it, I guess, more difficult to deal with this? Is this starting to have any plan or discussions or regulations?
Good question, and that's a very good observation. So far, of course, we share that idea, right? Is concerning how the political situation can affect all our discussions. So far, we haven't seen that. That doesn't mean we are not conscious of that, but so far we haven't seen a change in the willingness of countries to discuss about dark and quiet skies. In particular, I would say in the ITU, that hasn't been a change. So we are still struggling as much as we struggled before. Let's say it in a simple way. So in the ITU, we haven't seen a change, but the ITU is very particular. The ITU is very focused on the work people need to do. In COPWAS, we will see when we had the last scientific and technical subcommittee where there was the first discussion on dark and quiet skies, so the item on dark and quiet skies started. We didn't see any change other than some delegations were shrinked a lot, so the people kind of changed, but we haven't seen that so far, like a big change. But we are aware that that could impact all our work, so we are conscious of that. Yeah.
Anton, you're next.
Okay, thanks, Federico. It was a very interesting talk. I have two questions, if you don't mind. The first one is that we have received many of the scientists that are members of the scientific working groups from SKA. We have received an email in which they are asking about the possibility to move the frequency, the band 5 frequency. What does it mean? It does mean that the battle is lost, and then we have to shift our frequency band to, let's say, to lower and higher frequencies. What's your?
Yeah, that's a good question. No, what that means is that we are trying to have a good understanding of how our different science cases can be impacted. And what's important about this is because this is not a binary problem, right? It's not that we will have RFI or we will not have RFI. It will be a gradient and the question is how much RFI will be there or how much we will be able to mitigate it. And of course, it will depend on the science, right? If we are talking about a science case that uses interferometry and long baselines, long integrations, we are counting on, for example, having bore site avoidance in the mid site. We are counting on the national regulator to keep the beams of the satellites as far away as possible. So that all means that we will have this level of RFI. Now the question is, what kind of science will be possible with that level of RFI within the bands that belong to the satellites?
Okay.
That's the important conversation there.
Thanks for the answer. My second question concerns the bore site avoidance, in the sense that what you have said is that the results are quite promising, in the sense that there has been an improvement in a factor of 1,000, if I remember correctly.
Yeah.
What you said, but you have said that this is based on the direct communication with the satellite,
Yes.
with companies. Will there be a way to automatize this kind of contact?
Yes. Yeah. Yes, exactly. Yeah, I went too quickly through that, but thanks for the question because that allows me to expand a little bit more. The idea is that already in the US, NRAO has developed this. They were the first one to do this, and they have developed a system which they call ODS, Operational Data Sharing, I think is the name. And the idea is exactly that. It's an automatic system that has a server where the telescope inputs what frequency and where in the sky it will be observing with a certain schedule, and the satellite company queries that, and they automatically see, so they can say, okay, the SKAO is going to observe within this frequency range for this amount of time in these positions in the sky, for example. And they can pre-program all their satellites to do this bore site avoidance so that we see a mitigation in the level of RFI that we'll see. But that's exactly that. There are some caveats that it doesn't have an instantaneous response, right? So we need to load our observation schedule, and then it will take some time for the operator to actually implement this. So in principle, it works. There can be some corner cases that you say, well, if I want to do the observation now and it changes now, well, yeah, maybe that will not be so easy to do, but we are still working on this, right? It just started.
Okay, thanks.
I have a question quickly. In your point of view, how helpful are the satellite companies? And I realize maybe you have to be careful in how you respond to this. But for instance, do we have people that are set aside to actually work with you on this, or is this questions that we're kind of annoyed by, or I really, for instance, like the idea of having an astronomer working together with people there, for example. Anyways, anything you can say on that?
Yeah. No, it's a good question. It's a question that we get all the time, so there's no problem in answering it. And the answer is frank, right? I think they are very open to work with us within the acknowledgement that we are asking for something very difficult, and some of these effects are unintended, right? So the reflection from the sunlight, it wasn't something that was planned to do. So satellite operators are trying to figure out also how to mitigate that. And on the radio side is a bit simpler and trickier, because if you think on the regulatory part of the use of the radio spectrum, everyone knows the rules and we all play together. We clash a lot because we have different interests, of course, but we all play together, and that's normal work. Then when we go outside of that regulation into working in things like boresight avoidance, UEMR, which are things that kind of touch pieces outside the regulation, the discussion gets much more tricky, because sometimes we also need to be careful to not say you shouldn't be transmitting in these frequencies, for example, right? If we say something like this from the radio astronomy side, we are going to get a lot of very annoyed satellite operators that have the full argument to say, well, these are the frequencies that have been assigned to me to provide a service, to sell internet connection, for example. So, but we are very careful on both sides, on especially on the narrative and how we treat all of this, because we are trying to collaborate to find solutions that are balanced to be able to have the two things, right? Not recently, we were working on the posters for the Vienna conference in the UN in December, and one of the logos or the slogans that were there was turning on connectivity without turning off discoveries, or something like that. And I think that summarizes it very well, right? It's trying to say satellites bring good things also, because we all depend a lot on satellites, but at the same time, we need to do science, right? We have all these amazing instruments that are doing science, and we need to find a way to have everyone at least equally impacted, let's say.
Yeah, thank you. On that note, actually, if I don't mind, I see there is no more hands here, but please interrupt me. In outreach events, I often get the question, will people be able to continue doing astronomy? So for instance, a student asking you, is it even useful going into astronomy at this part? I guess my question is, are you hopeful with all the work you're doing, and what would you say to such a student?
Yeah. No, look, in terms of optical astronomy, definitely yes. Optical astronomy, as we were saying before, it depends a lot on the different telescopes and how reflection from sunlights affect them, right? So that's a different discussion, and I won't go too much into that because it's not my field. And on radio astronomy, the radio spectrum is very large, right? So if you saw all these bands there, and there's a lot of room in there for everyone. The challenge is that, of course, the use of the radio spectrum keeps increasing also. So I don't think it's going to be a showstopper at any point, but it's going to get more difficult. That's for sure. So, but also we are seeing other options, right? People are talking about going in the future to the moon. So that's also an option in the future, of course, because at the moment we have a lot of capabilities on Earth that are way much more than whatever we can put on the moon. So our focus is right now on Earth, and now we expect that there will be great science with the SKO for a lot of years, not without its challenges, for sure, but I need to work, right? So
Yeah.
yeah.
Well, thank you so much. Are there any more questions? Otherwise, I see we have reached our hour and a little bit over. So
Muchas gracias.
Thank you very much, Federico. We close
Thank
the
you.
talk here.
Muchas gracias, Federico.
Muchas gracias a todos. Saludos.
Nos vemos
Gracias.
pronto. Adiós.
Gracias. Hasta luego.
Saludos por allí.
Chao, chao.